Welcome to video lecture on Internet of Things. In this session, we'll study about data analytics for IoT. In the module 4, we are going to study about an introduction to IoT data analytics, and we are going to study about tools and technology used for IoT data analytics. Then we are going to study how to secure IoT. That is, what are the challenges faced by the IoT data analytics. First, we'll study about an introduction to data analytics for IoT. In this session, we introduce the subject of analytics for IoT and discuss the differences between structured and unstructured data. We also discuss how analytics relates to IoT data. In the world of IoT, the creation of massive amounts of data from sensor is common and one of the biggest challenge, not only from transport perspective but also from a data management perspective. For example, a deluge of data can be generated by IoT, which is found in commercial aviation industry, and sensors that are deployed throughout the aircraft. Modern jet engines are fitted with thousands of sensors that can generate a large amount of data, about 10 GB of data per second. Modern jet engines are equipped with nearly 5,000 sensors. A twin engine commercial aircraft with these engines operating on average 8 hours a day will generate over 500 TB of data daily. And this is just the data from the engine. So aircraft today have thousands of other sensors connected to the airframe and other systems. A single wing of a modern jumbo jet is equipped with 10,000 sensors. So we cannot imagine the data generated by a single aircraft engine. So there are so many aircraft engines working every day. So we can think how much data is generated as well as how to handle it, how to get the knowledge or information from the data generated by this jet engine is the challenging task. Another example for generating the data by IoT is utility industry. Even moderately sized smart meter networks can provide over 1 billion data points each day. These two examples highlight the need for data analytics for the data generated by IoT. Analyzing the amount of data is most efficient in the most efficient manner possible falls under the umbrella of data analytics. Data analytics must be able to offer actionable insights and knowledge from the data, no matter the amount of data or style of data, in a timely manner, or the full benefits of IoT cannot be realized. So, sensors are going to generate billions of data that depends upon the data analytics, how we analyze the data to get the knowledgeable information from this sensor generated data. Not all the data are same. They can be categorized. They can be analyzed in a different way based on the category. Depending on how data is categorized, various data analytic tools and processing method can be applied. The two important categories from an IoT perspective are whether data is structured or unstructured and whether it is in motion or at rest. So main thing you have to consider, you have to categorize the data generated by IoT devices into structured data and unstructured data, or the data is in motion or data is in rest. These are the two important things to be considered while choosing the tools and processing method of data analytics. Structured data and unstructured data are important classification as they typically require different tool set from the data analytics perspective. In the figure, you can see the structured data and unstructured data. So, structured data are organized in the form of spreadsheet or databases, whereas unstructured data does not have a particular format or does not conform to a particular model. Example for unstructured data are text, image, video, or speech. Structured data means that the data follows a model or schema that defines how the data is represented or organized, meaning it fits well within a traditional relational database management system. In many cases, we will find structured data in a simple tabular form. For example, a spreadsheet where data occupies a specific cell and can be explicitly defined and referenced. IoT sensor data often uses structured values such as temperature, pressure, humidity, and so on, which are all sent in a known format. They are the example for structured data generated by an IoT sensors. Structured data is easily formatted, stored, queried, and processed. From custom script to commercial software like Microsoft Excel or Tableau, most people are familiar and comfortable with working with structured data. It is easy to handle the structured data than the unstructured data. It is easy to handle or organize the structured data, and a wide array of data analytics tools are readily available for processing the structured data. Whereas unstructured data lacks a logical schema for understanding and decoding the data through the traditional programming means. Example for unstructured data are text, speech, images, and video. As a general rule, many data that does not fit neatly into a predefined data model is classified as unstructured data. According to some estimate, around 80% of a business data is unstructured. Since the 80% of the business data is unstructured, data analytics method that can be applied to these unstructured data such as cognitive computing and machine learning are getting more attention nowadays. With machine learning applications such as natural language processing or NLP, we can decode speech. With image or facial recognition application, we can extract critical information from the still images and video. Smart objects in IoT networks generate both structured data and unstructured data. The handling of unstructured IoT data employing machine learning technique is getting more important since the data generated by business is 80% unstructured. The structured data is more easily managed and processed due to its well-defined organization. On other hand, unstructured data can be harder to deal with and typically requires very different analytics tools for processing the data. Being familiar with both of these data classification is important because knowing which data classification becomes important for choosing appropriate data analytics solution for getting the knowledgeable information from the data generated by IoT. Second way of categorizing the data generated by IoT is data in motion and data at rest. In most of the networks, data in IoT networks is either in transmit, that is data in motion, or being held or stored, that is data at rest. Example of data in motion include traditional client server exchange such as web browsing and file transfer and emails. Data saved to a hard drive, storage array or USB drive is the data at rest. From an IoT perspective, the data from smart object is considered data in motion as it passes through the network or it route to its final destination. This is often processed at the edge using fog computing. When data is processed at the edge, it may be filtered and deleted or forwarded on further processing for possible storage at the fog node or at the data center. Data does not come to rest at edge. When data arrives at the data center, it is possible to process it in real time just like at edge while it is in still motion. So you can process the data either when the data is in motion at fog or using fog or edge computing, or you can process the data at the data center when the data is in rest. Tools with this sort of capability such as Spark, Storm and Flink are relatively nascent compared to the tools for analyzing the stored data. Data at rest in IoT networks can be typically found in IoT brokers or in some sort of storage array at the data center. Mermaid of tools, especially tools for unstructured data in relational databases, are available from a data analytics perspective. The best known tool is Hadoop. Hadoop not only helps with data processing but also in data storage. The IoT data generated by smart objects become important when the analysis of this data leads to actionable business intelligence and insight. So we'll look into IoT data analytics now. The data analysis is typically broken down into different types based on the types of result they are going to produce. There are four types of data analysis results. One is descriptive, the second one diagnostic, third one predictive, and last one prescriptive. In the diagram, we can see the four types of data analysis results. First one is descriptive, means what is happening. It gives an insight, that is what is happening. Diagnostic, why did it happen? Predictive, we will think what is likely to happen. We are going to predict the feature from the data generated. Prescriptive, what should I do about it? So what are the actions to be taken by analyzing the data? These are the four results that is we are going to get by the data analysis. So then after the analysis, for the analysis we are going to use big data technologies for collecting, integrating, processing and aggregating and for visualizing. So data may be generated by smart objects, may be raw or processed data. It may be mobile, internet, machine and sensor, usage, video, social media, events, alarms, geolocation, CRM or ERP, emailing and messaging, relationship and social influence. So the data may be these data. Then we apply some big data technologies for collecting, integrating, processing and aggregating and visualizing. Then the data analysis can result in four types of analysis, that is descriptive, diagnostic, predictive and prescriptive. Now we'll look into what is descriptive data analysis result. Descriptive data analysis tell us what is happening either now or in the past. For example, a thermometer in a truck engine reports temperature values every second. From a descriptive analysis perspective, We can pull this data at any moment to gain insight into the current operating condition of the truck engine. If the temperature value is too high, then there may be a cooling problem or the engine may be experiencing too much load. Second type of data results we are going to get by data analysis of IoT data is diagnostic. When we are interested in why diagnostic data analysis can provide the answer. Continuing with example of temperature sensor in the truck engine, we might wonder why the truck engine failed. Diagnostic analysis might show that the temperature of the engine was too high and the engine was overheated. Applying diagnostic analysis across the data generated by a wide range of smart objects can provide a clear picture of why a problem or event occurred. Third analysis result is predictive. Predictive analysis aims to foretell problems or issues before they occur. For example, with the historical values of temperature of the truck engine, predictive analysis could provide an estimate on the remaining life of certain components in the engine. So, before something happens, we have to give some estimate, that is called predictive analysis. This component could then be proactively replaced before failure occurs, or perhaps if temperature values of the truck engine start to rise slowly over time, this could indicate that need for oil change or some other sort of engine cooling maintenance. So we can take action and we can stop some damage or failure occurrence by the predictive analysis. Fourth type of data analytics result is perspective. Prescriptive. Prescriptive analysis goes a step beyond predictive and recommends solution for upcoming problems. A prescriptive analysis of the temperature data from a truck engine might calculate various alternatives to cost effectively maintain our truck. So this calculation could range from the cost necessary for more frequent oil changes and cooling maintenance to installing new cooling equipment on the engine or upgrading to lease on a model with more powerful engine. So prescriptive analysis goes ahead of predictive analysis. That is, it gives a more alternative solution for the problem, how to maintain it in a cost effective manner. Both predictive and prescriptive analysis are more resource intensive and increase complexity, but the value they provide in such greater than value from the descriptive and diagnostic analysis. The four data analysis types can be ranked based on the complexity and the value increases. Descriptive analysis is the least complex and at the same time it offers least value. On other hand, prescriptive analysis provides the most value but it is the most complex to implement. So in the figure you can see the four analysis types and how they rank as a complexity and the value they increase. So we can see descriptive analysis has the lower rank. Next comes the diagnostic analysis. At the third level we have the predictive analysis. At the top level we have prescriptive analysis. That is, they provide higher value data as well as it is very difficult to or complex to implement. Now we'll see the challenges we are going to face for IoT data analytics. Traditional data analytic solutions are not adequate. While rational databases are still used for certain data types and applications, they often struggle with the nature of IoT data. So we have studied 80% of the business data is unstructured. Relational databases only suitable for structured data. So what are the challenges we are going to face for IoT data analytics? We are going to study now. IoT data places two specific challenges on traditional relational database. One is scaling problem. Due to the large number of smart objects in the most of IoT networks that continually send data, relational databases can grow incredibly large and very quickly. So the database size may grow very large at a smaller duration of time. That is, it can grow very huge data very quickly. This can result in performance issues that can be costly to resolve, often requiring more hardware and architectural changes. So it is difficult to handle the data base which grows very quickly in the relational databases. It is more costlier and it requires hardware, more hardware and more change in the architectural design. Second type of challenge is volatility of data. With relational databases, it is critical that the schema can be designed correctly from the beginning. Changing it later can slow or stop the databases from operating. Since the large amount of data will be coming in, we may have to change the relational database schema, which may slow down the process as well as it may stop the database operation itself. Due to the lack of flexibility, revision on the schema must be kept minimum. IoT data, however, is volatile and the data model is likely to change and evolve over the time. A dynamic schema is often required so that data model changes can be made daily or even hourly. So, large amount of data will be generated. Hence, we may have to change the schema every day or even hourly. So, dynamic schema is required oftenly that changes the data model. So, hence the relational database may not be suitable. To deal with challenges like scaling and data volatility, a different types of database known as NoSQL is being used. Structured query language is the computer language used to communicate with RDBMS. NoSQL database is a database that does not use SQL. It is not set up in traditional tabular form of a relational database. NoSQL database do not enforce a strict schema and they support a complex evolving data model and are also inherently much more scalable. So whatever the two challenges we faced in the traditional database system was scaling problem and volatility of data. So NoSQL database certainly can handle volatility and scaling problems. In addition to the relational database challenges that IoT imposes with its high volume of smart object data that frequently changes, IoT also brings challenges with live streaming nature of its data. In IoT, the data generated by IoT, we have to process the data at real time. That is, live streaming nature of its data makes the data analysis challenging. Streaming data which is generated as smart object transmit data is challenging because it is usually of very high volume and it is valuable only if it is possible to analyze it and respond to the data at real time. The data generated by IoT devices or smart objects should be analyzed and should be responded in real time. Otherwise, this data becomes useless or less valuable. The market for analyzing streaming data in real time is growing fast. Major cloud analytics providers such as Google, Microsoft, and IBM have streaming analytics offerings, and various other applications can be used in house. Another challenge that IoT brings to analytics is the area of network data, which is referred as network analytics. So what are the challenges IoT data is facing is one is scaling problem, second one is volatility of data, third one is analyzing the live stream data, fourth one is network analytics. So there are four main major challenges the IoT data analytics is posing. So in this session, we have studied about an introduction to data analytics for IoT. That is, we have studied about types of data, that is structured or unstructured data, or data in motion or data at rest. Then we studied about data analytics overview, that is the types of data analytics results. Then we studied about IoT data analytics challenges. In the next session, we'll study about machine learning, which is helpful for IoT data analytics.